All right. So in this video, we're going to generate the surface coordinates of a helical pipe in elliptical cross section of major and minor radii, 1 and 0.5 respectively, and with a central helical curve defined by the following parameterization in T of 0 to 6. 0 to 6 pi. Part 1, we're going to create a code using closure. We're going to make a higher order function that returns functions that calculate the Frenet-Serret T equals dr over ds, which is the tangent, and n equals dt over ds, which is the normal vectors for the helical curve. Starting off, we're going to tackle our imports. All right. Next, we are going to define our vector. Vec equals NP array. We're just going to set values of 1 and 0 for now. These are parentheses. Oh boy. We're having difficulty already, ladies and gentlemen. There we go. Don't mind me. So that'll return our vector in the form of 2 rows and 1 column through this reshape function, as you can see here. All right, so next we're going to define a function for a rotation to rotate a matrix by an angle of theta, or a value of theta. So first we have to define our values. So sine equals J and P of sine at theta, and then cosine equals J and P cosine at theta as well. And then we're going to return our array, which is going to be cosine, negative sine, and then sine, cosine. Cool. All right, now that we have our definition for our rotation matrix function in terms of theta, we can define we can basically create a bunch of points or many thetas from, NP on the full circle. So we can take an area from 0 to 2 pi. And then we could say like 200 points on that full circle. And then we're going to disable the endpoint so that we don't end up plotting. Gosh, I can't type. Okay. We're going to disable the endpoint so that we don't end up plotting 0 and 2 pi on the same chart. So now we're going to create basically like our storage system. So XY values is equal to that. And now we're going to create a for loop for our each rotation. So for theta and many thetas, for each of these, we're going to create a new value for a rotated vector. And this is going to equal our function. So let's just copy and paste that. I'm lazy. And we're going to vector multiplier dot product that with our base vector. And we are going to continuously add those new rotated vectors into our XY values. By saying XY values append cool. So now we're going to replace our XY values by I don't know how to, yeah, concatenate. Yes. Thank you, Python. So we're going to concatenate or like put in a series all the values. Shoot, I already forget how to do this. Yes. Maybe. Okay, that worked. So now we're going to go ahead and make our subplot. So fig equals make underscore subplots. Fig dot add scatter. We're going to have x equal XY values at 1 or 0. And then y is going to equal XY values at 1. Node markers. Okay, there's our graph. I'm actually going to make this. Oh boy, not like that. There we go. Okay. So there is our circle with our rotated vectors for all 360 degrees or over the course of 2 pi. So now I'm going to show you how to kind of stretch the ellipse a little bit. So forget what this is. Let's go with that first. Okay, and then we're going to stretch our XY values. So stretch XY values. It's going to be stretch matrix vector multiplied with the XY values. So, all right, now if we take this guy down here, and add another scatter. This works. Oop. Ah. Okay. Stretched it, but in the wrong way. Big update X axis. What is it? Just 3? No. Oh, cool. That looks great. Oh, sorry. Having a little difficulty here. Okay, that looks better. So now we've stretched our data points in the x direction. I believe by a factor of 2. Let's see what happens when we change it to 3. Be sure to get wider. Yeah, so it'll stretch based on the value that you type in here. So I'm actually going to add, so this looks a little better. Right. There we go. That looks a little better. Forget if I put this here or not. Sweet. Okay. So next we're gonna try and rotate this kind of stretched ellipse. So we're gonna rotate, stretch, XY values. We're gonna do that by taking our rotation matrix function. Then we're going to put it in terms of a set value for pi, or not a set value for pi, but like a set value that we're going to rotate it by. So we'll start off with pi over 6. And then we're going to dot product that with our stretch XY values. Okay. Let's see if I can actually plot this. Okay. Okay. So as you can see, we've rotated it by a factor of pi over 6. And we could change that if we wanted to. Let's do like pi over 3. Rotate a bit more. Pi over 2. So whatever factor you put in here, that's how much it'll rotate. Here's the fun part. Here's where we're gonna try and make our helix. So we're gonna generate a certain amount of values for S. So let's go back up here and grab this guy. Went something like 1,500 points. Our X is gonna be our cosine. Ooh. I forget how to do this. Y equals NP sine. Is it of S? It might be of S. And then Z is gonna be it's gonna be S divided by it's gonna be S generated over a course of 2 pi. So now that we have our conditions for our plot, we're gonna make it so fig equals add. Wait. Why am I? Yeah, sorry. Make subplots. I struggle hardest with making these things. Then we're gonna have rows. Columns. And then sorry. Specs. Where is it? Okay. X is going to equal X. Y is going to equal Y. And then Z is going to equal Z. And then let's expand it a little bit. Maybe do 750 by 750. Maybe. No. That's a big no. Oh. Huh. That's another big no. That's why. We're gonna pretend that didn't happen. Okay, so this is what it should look like over the course of 2 pi. But if you expand it over the course of like 4 pi, then it'll tack on another addition on the top. Then 6 pi, which is the one we desire based on the problem statement, it'll look something like this. And I'm gonna not make it look as thick. Let's do a line. So that is our helix. Now that we have our beautiful graph of this helix here, if we set radius, say 5, why did that? Sorry, I lost my train of thought. If we set a radius of 5 and a change in the z direction of 0.5, then we could do something pretty cool with this this here helix. So we're going to make some functions using the Frenet-Serret equation, and then we're going to wrap this thing in insulation. It's going to become a water slide. So first we have to make a helix function. We're going to put it in terms of our s, our radius, and our change in z. Okay. Shoot, I forget the syntax. Gonna take me a minute to type this out. Wait, I don't need this. So I already have these as functions, right? No, I don't. Haha, psych. Cool. Actually, I messed up here. This is supposed to use jacks here because we're gonna have some functions that we need to use, such as the Jacobian later on. So this needs to be in terms of jacks. Okay, so now we can define our Frenet-Serret. Okay, so encased in this, we're going to have like our base function, and then we're going to have our tangent function and our normal function, and then we'll be able to set up basically like a function of functions, and it'll be comprised of our tangent and normal values, and that's how we'll be able to express the things that we want for part A. RDS, those checks. Echo being of R. I'm gonna throw these in here. So our resulting derivative function is going to be that guy. Okay. Return ERDS result for A and P knowledge. One probably has to be in parentheses. Of the RDS results. So let's get rid of this, see what happens. Oh, I see. There we go. Okay. Just wondering why it was yelling at me. Okay. Um, okay. So now we're going to have pretty much the same thing as the tangent for the normal. So we're going to have tangent ds results equals the tangent ds times of s. Return. I don't want to type that. Cool. So it should give us functions for our tangent and normal functions. Okay, the last thing we want our Frenet-Serret to do is return our tangent and normal. Okay, so now we can set our tangent and normal equal to What am I looking for? Set our tangent and normal in terms of Frenet-Serret. Gosh, damn, thank you. Once again, Python. Lambda S. And then it's going to be in terms of, I don't know if I need parentheses there, but these three guys here. Wait, sorry. This whole guy here. Cool. Now if we just return like tangent or normal, you can see that the tangent and the normal are defined as Frenet-Serret equations. So we have a function inside of an output here. So that is all the deliverables for part A, or sorry, part 1. Using closure, explain and code a higher order function that returns functions that calculate the Frenet-Serret tangent and vectors for the helical curve. So part 2 of this assignment is to explain and code a function that calculates a surface point on the elliptical cross section of the helix. To start off, we're going to define a new function. So it's going to determine the surface of this helix. So I'm just going to call it surf. It's going to be in terms of s and theta. We're going to have three variables for this, n, t, and b. So n is going to be our normal. Oh my gosh. I hate when my keyboard does that. N is going to be our normal for at any point on that helix. T is going to be our tangent at any point S on that helix, and then B is going to be our what do you call it? B is going to be our cross vector between N and T. Okay. Okay. So the next thing we have to establish, so we're going to have cross section major and minor radii of 1 and 0.5 respectively. So our next course of action is to establish our major is going to equal 1, and then our minor is going to equal 0.5. And then we're going to do something similar that we did up here, where we do a vector rotation. So we're going to take our rotation matrix formula that we already have. Actually, I think I should do this. This one's going to be vector multiplied with what was it again? Oh, it's this guy. JMP array. We're going to rotate this this reshaped vector here. It's just going to be set just a V, I guess. Okay, I actually forgot. We need to return so we're going to do V0 times our R major times N plus V of 1 times R min or R minor times B plus our helix function. There we go. All right, next part, we're gonna create a surface vector function. So surf vec equals JMP vectorize. Surf, our surf function, signature, zero, zero, I don't know, I think it's this thing, 3. That's going to be our signature type. See if that works. Nope. Maybe. Sweet. Now we want to create an array of S's and thetas. For thetas, we want to do, where is it? Gosh. This guy. Use Jax though. And we're going to go to 6 pi. That's not the right one. And then for thetas, we're going to do the same thing, but do 50 of them and do 2 pi. What this is going to do, this tells us our amount of circles we're going to have, or ellipses going around our helix, and then the amount of vector cross sections that we're going to have, or just like, I guess, points of interest. Okay, now we have change in S, or delta S equals our S is at 1 minus our S is at 0. And then our delta theta is equal to our thetas at 1 minus our thetas at 0. Okay, now if we shift n around some thetas and delta S, we'll see we've developed an array for both of these outputs. So now we have to establish the points that are going to be going in our surf equation. So now we can use the surf vec function And then with SS, we're going to have this syntax. And then for thetas, we're going to have this guy. This should put our SS points and theta's points inside of one. Now we can return surf points. So now we have all of our points on our surface here. So part 3 of this assignment is to vectorize the function in part 2 and generate a plot of the surface by discretizing T and the elliptical cross section. So from part 2, we have our surface points. So we have the plot of our surface, or sorry, we have a function that gives us points on the surface. So now, let's start off with this guy here. So we're going to create a plot of all of these surface vectors, cross sections, and such, and we're going to plot probably about 1,500 points. That seems pretty good. We're going to set our x, y, and z equal to the helix function. S, what was it? S, rad, z, change. Okay. Okay. So our NS value, so I just restated these here, but they were already being used. Where was it? Right here. So this is our S value. This is our NS, or sorry, this is our NS. This is our N theta. So I just restated these down here. We're going to set our X, our Y, and our Z for this for loop. Equals our surf points function in terms of S IDX, and leave the other two open. And this is for each point of S on our helix, and then we're going to define each point for theta on our helix as well. Make this one look funky. I can't stand when it does that. Okay. Copy and paste this, honestly. We're just doing the same thing for theta, except we're putting it in the second slot instead of the first. Sorry. Why is this giving me an error? Oh, gosh. Okay. Now, this guy going. See if this works. Ooh, not quite. We're missing something. Supposed to be line color, guys. Tried to get fancy. All right. It worked. So now we can make our plot. So I'm just gonna steal this guy here. See if she works. Cool. So this is our helix. You can see the blue line in the middle. That was our original helix. Now it is surrounded by ellipses and cross-sectional vectors. So here it is. Okay, so I believe that's everything we needed for part 3. Just vectorizing the function and generating a plot of the surface by discretizing T and the elliptical cross section. So here that is. Part 4 is calculate the surface area by summing the magnitude of the cross product of the vectors, defining discrete parallelograms in part 3. Then compare against multiplying the total arc length of the helix by the perimeter of the ellipse. Okay, so now we're gonna run the Jacobian on the surf function. So surf jack equals jack's Jacobian surf. I forget how to do this. Where's my other Jacobian? Yeah, I think it's just at the function. Maybe. Oh boy. Uh, yeah, that worked. This is actually supposed to have, I know this is supposed to have this in here. Man, I keep screwing this up. Okay. So now we're going to create a function for the cross-sectional area. So surf for the area in terms of s and theta. Vec, so it's our derivative of our vector, d theta, sorry, d vec ds, and d vec d theta is equal to surf vec of s theta. Okay, and this is going to return the function of cross vectors between our dvec ds and our delta s function, and then dvec d theta times our delta theta function. Okay. Looking good so far. Now we are going to vectorize the surf dA. So JNP dot, sorry, yeah, JNP dot vectorize. We're gonna get wait, this isn't right. Don't think this is supposed to be here, so let's go back up here and get the little copy paste going. Except we're going to leave this open. All right, so that should vectorize our surf dA function. Okay. Now we're gonna make it spit out a sum here. This guy. I think we're supposed to, I'm looking for some specific. Where is it? What in the world? Where'd it go? Oh, here it is. Probably would have been quicker just to type it. But... Okay. Okay. I'm gonna do -1 instead of leaving it open this time. Oh. Okay. Uh, that'll do it, wouldn't it? Cool. You get a value of 458.8454939. Okay, now we're going to run the Jacobian on the helix function. Okay. Okay, so this is to find the differential arc length for the helix function. Oh shoot. Whoopsie daisy. This guy is going to return J and P. I forget what it is. J&P dot lin and alg dot norm. Helix. What was the helix dvec ds. Yes. This guy's in terms of our normal helix function, S rad Z change. And then we're going to multiply that by delta S. Cool. Okay. Now we're going to basically do the same thing as this, except we're going to be vectorizing this guy. Okay. Okay. There we go. Actually, this is supposed to be like that. So now we can find the total helix arc length. Actually, I just noticed something. Why did it do that? Okay. I don't know why I didn't just do that in the first place. That's right. Actually, this is supposed to just be that. I'm pretty sure. We gotta change this guy too. That should be straight. Yeah. So there's one more. So we can copy that guy and stick this guy in there. Right. Okay. Now we can take this guy and do it for our ellipse, our ellipses. So ellipse dvec ds. Take the Jack's Jacobian. We're gonna do it with our surf function. Okay, now we can Do the same thing for the ellipse as we did for the helix. Theta. And then ellipse. I think it's theta. Cool. Okay, now that we have specified the differential arc length for the ellipse and the helix, now we can do something similar we did here for the ellipse as well. So ellipse, ellipse. Okay, that should do it. Okay, and then one more thing to do our sum. So we're just gonna do the same thing that we did the past two things for the ellipse. Just basically copy everything over from the helix. Change the parameters. Thetas. Okay. So the last thing to do in order to get area, area compare is equal to the total helix arc length, this guy, times the total ellipse arc length. Okay. So and then what else did I want? This guy. Okay. So as you can see, the area comparison is identical to the answer we got up here. So I think that's all for part 4. Just compare against multiplying the total arc length and of the helix by the perimeter of the ellipse. So yeah, so we have our compared area, and it's the same as our estimated area from us doing it using the differential area method. So that is all for this homework. Thank you all for watching.